Namaskar and welcome back to a new session on concrete engineering and technology, where we are talking about basic principles in concrete science and engineering and developing a framework where the different topics which are of importance in modern day construction as far as concrete construction is concerned can be taken care of and studied. Some of the issues that we are trying to deal with are in terms of special and high performance concretes, their quality control and testing, especially related to performance based thinking, durability and maintenance. And we are trying to study the fundamentals, proportioning of concrete mixes, stages in concrete construction, special concretes, mechanisms of deterioration, reinforcement and maintenance. Now, we will continue our discussion on special concretes today, and like we have said, what is a special concrete? It could be in terms of the material that we use other than the normal sand, ordinary Portland cement, water and coarse aggregate. It could be in terms of the properties that we expect from the concrete in terms of strength, workability and so on. It could be in the terms of the method of casting, placing or curing. Shotcreting is an example of that. It could be in terms of the environment in which the concrete is cast, for example, underwater and so on. As far as materials are concerned, it could be the use of fibers, high volumes of fly ash and things like that. As far as properties are concerned, like I mentioned, it could be strength, workability, durability and so on, except that durability is a very difficult property to quantify. As far as methods is concerned, it could be shotcrete, it could be roller compacted concrete. As far as the environment is concerned, it could be underwater as I mentioned, it could be hot or cold weather and so on. So, now these are some of the examples of special concretes, and today we will focus our attention on mass concrete. Now, how do we define mass concrete? There is no watertight definition. There is no definition that can be given that okay, this is what mass concrete is, except that the connotation is that it is a large volume of concrete. If we want to define it technically, the ACI and other documents will help us, and we can call mass concrete as that which requires special attention to take care of thermal stresses that may arise in concrete due to the liberation of the heat of hydration of cement and the ensuing volume changes. So, we are looking at a concrete where the exothermic reaction of hydration of the ordinary Portland cement, which is an integral part of concrete, causes temperature rise to such an extent that special measures need to be taken to take care of that temperature rise, because that temperature rise is accompanied by formation of stresses within the concrete. Maybe it could result in cracking and also volume changes. So, if there is a special need to specifically take care of the thermal stresses, the temperature rise and so on, then that can be called mass concrete. Now, it is interesting to see that now we are taking up mass concrete as a special concrete, where we are trying to invoke temperature rise, development of thermal stresses and so on as a very special property of concrete, which normally does not require attention, but acquires some significance in certain contexts. So, that is what is going to be the subject of discussion today. Such concretes could involve pours of large volumes of concrete with relatively small surface area, and gravity dams can be cited as an example of such construction. So, dams are an example where there is a very large volume of concrete cast in every pour. Dams are not cast in a single pour, they are cast in thousands of pores. So, but each pour is itself a large volume of concrete and cast in a manner that the surface area is very small, relatively speaking, and we will see these discussions coming up again and again as we go along in our discussion today. Another situation where mass concrete considerations will apply would be in cases where the volume of concrete poured could be relatively smaller, it could be a medium pour in terms of volume, but the concrete used could be high strength concrete, and this high strength concrete has a large amount of cement, and if it has a large amount of cement, the total amount of heat that is liberated during its hydration is large, and therefore, again the issue of temperature rise, thermal stresses, volume changes, all this has to be taken into account as far as the construction process is concerned. These constructions could involve piers or anchorages, where sometimes we try to use high strength concrete in modern day construction. Now, we have been talking of thermal stress. Now, what is a thermal stress? It is the stress generated in concrete on account of shrinkage and volume changes related to the release of the hydration of cement. That is very much related to internal and external restraints, as we shall see in our discussion as part of this module of concrete discussion. Now, a little bit of historical background. Before 1900, the construction of large structures like dams was not very organized, and we do not have too much recorded information about it, but between 1900 and 1930, that is about 100 years ago, 80 to 100 years ago, construction of dams such as the Arrow Rock Dam in 1915, the Dalton Dam in 20, the Theodon Roosevelt Dam in 1911 was greatly accelerated, and a lot of information came about to concrete engineers or civil engineers. And around 1930, the Hoover Dam was in the early stages of planning, and because of the exceptional size of the Hoover Dam, investigations were a lot more elaborate than any other constructions undertaken previously using ordinary Portland cement. Of course, after the 1970s, when the behavior of concrete was much better understood, the construction equipments had evolved, roller compacted concrete and so on came into vogue, came into use, and it became one of the promising alternatives as far as placing mass concrete is concerned. Now, before the discussion on mass concrete becomes technical or very technical, let us revisit some of the relevant fundamentals once again. What is the composition of ordinary Portland cement? We know that it consists of tricalcium silicate, dicalcium silicate, tricalcium aluminate, tetracalcium aluminoferrites and gypsum. And the percentages that are given here are representative. A cement could contain 45 to 75% of C3S, 7 to 32% of C2S, about 5-10% of C3A, and up to 18% of C4AF, in addition to gypsum. Now, we also know that once water is added to the cement, all these phases undergo hydration, and these phases liberate different amounts of heat as far as the heat measured in, let us say, kilocalories per gram of these phases is concerned. And therefore, for a given cement, we can work out the total heat liberated in terms of kilocalories or joules per gram or per kilogram, depending on the chemical composition of that cement. We must remember that this heat is liberated over a long period of time. Hydration does not stop in 3 days or 7 days or even 28 days for that matter. It continues for a much longer time, and how long that hydration continues also depends upon the individual phases. These phases react and hydrate at different rates. As far as concrete is concerned, the hydration may continue for a very long time if supplementary cementitious materials like fly ash or blast furnace slag is used, and then this directly impacts the rate of heat liberated, and this is something very important as far as our discussion today is concerned. As far as C3A is concerned, the tricalcium aluminate, it is the largest single compound contributor to the evolved heat, followed by C3S and C4AF, which are about equal, and finally C2S. C3S hydrates and hardens rapidly and is largely responsible for the initial set and the early strength, and also therefore the early heat. C3A also contributes to early heat. C2S hydrates and hardens slowly and is largely responsible for the strength increase beyond, let us say, a week or 10 days, and that is also true as far as the heat liberated on account of C2S hydration is concerned. So, in fact, depending on what construction we are doing, we may like to control the chemical composition of the cement that we use. If we are using a concrete where we need a lot of strength, we would like to increase the C2S and the C3S, but given the fact that C3S is not friendly as far as heat liberated is concerned, we may like to increase the C2S content. But we must understand that the hydration in C2S will be slow, and therefore, the strength development could be slightly slower, and if we are willing to live with that, that is all right. This diagram here shows a rough picture of the rate of heat evolution and also highlights some of the phenomena that are occurring at that point in time. For example, initially there is the C3S and the C3A hydration, which is in a few minutes. Then there is an initial set, and finally C3S hydration continues, C3A enters into a secondary hydration phase, and so on and so forth. Now, coming back to the fundamentals and bulleting them, noting them in points. Hydration of cement is a highly exothermic reaction. So, there is a lot of heat liberated when ordinary Portland cement hydrates. The heat liberated causes the temperature of the concrete to rise, unless that heat is somehow removed. So, if we cast a block of concrete which has cement, that heat that is liberated over a period of time will cause the temperature of that concrete to rise, unless the situation is such that the heat that is liberated is also removed from the concrete and dissipated into the atmosphere. We must also remember that concrete is cast against formwork. Very often we have lifts of concrete, which means that a concrete is placed on top of another concrete. So, the bottom of the concrete is not in contact with the formwork, but with a previously placed concrete, or sometimes PCC, that is the plain concrete, or ground, or any other material. As far as formwork is concerned, it could be plywood, steel, or any other material that we may choose to use. And then there is a exposed surface. Most of the time concrete has an exposed surface. And now these surfaces of concrete play a very important role in dissipating the heat, and that is what will be another subject of discussion today. Strength development in concrete is a gradual process and is intrinsically linked to the hydration of cement. Thus, the properties of concrete at early ages change very rapidly. we have drawn this picture repeatedly, that the strength of concrete changes like this, if this is time and this is strength. What we are talking of as far as mass concrete considerations is concerned is in the early stages, and at this point in time or in this period of time, the properties of concrete are changing very rapidly. And therefore, if something is of interest to us at this point in time, we must remember that the properties of concrete at that point in time are here and not here, which is the property that the concrete will acquire in a fully mature or a fully hydrated state. Continuing our discussion, depending upon the geometry of the member or the portion of concrete being cast, the temperature of the core of a large block of concrete will be higher than the portions close to the surface. If we cast a concrete block like this, I am showing it as a two-dimensional picture. Depending on the size of this block, the temperature of this plot, that is the core of the concrete, will be very different from the temperature of the surface anywhere. And we discussed earlier that this surface could be in contact with formwork here, or it could be in contact with the ground, or it could be exposed to air. So, these four surfaces here, that is if we call them as 1, 2, 3 and 4, 2 and 4 we have reason to believe that will be similar, but 1, 2 and 3 there is no reason to believe that the temperatures at these surfaces will be the same. And there is no reason to believe that these temperatures at the surface will be the same as the temperature in the heart of the concrete. All this discussion assumes that the concrete block has a certain size. If the size is very small, then of course, the heat is being taken away as the concrete is being cast, or as the concrete is hardening, and the temperature differences may not be substantial. Now, the difference in the temperatures in the core and the portion close to the surface sets up thermal gradients, which are the root of mass concrete related issues. So, if these thermal gradients can be avoided, a lot of our problems as far as mass concrete is concerned can be solved. Now, let us understand this a little better through another example. Let us consider this block and compare this with this very thin slab. We may say that the volumes of these two are the same, and there we realize that the block has a lower area to volume ratio than the slab. That is, for a given volume, the surface area of the block is much smaller compared to that of the slab, or the surface area of the slab is larger than that of the block that is shown here for a given volume of concrete. Now, if the same amount of heat is liberated in the two cases, it is easier removed from the large surface of the slab than from the block. The heat is dissipated into the atmosphere or the earth through the surface which is in contact with it. The top surface is in contact with the atmosphere, the bottom surface is in contact with the earth or the previous lift of concrete and so on, and the sides are in contact with the formwork. So, the heat is dissipated through these surfaces, and in the case of slabs that is much easier because the surface area is larger. Further, given the geometry, the thermal or temperature gradients in the block will be a lot more severe than in the slab, because in the slab the heat is being removed relatively quickly, because this dimension is small. So, the temperatures in the middle here and the temperatures at the surface may not be very much different. This is not the case in the case of a concrete block, where this distance is substantial, and therefore, there is reason to believe that the core will become hotter than the surface. Now, let us take an illustrative example and consider a 2 meter by 2 meter by 2 meter concrete cast against the ground. Volume of this concrete is 8 cubic meters, and the surface area, that is 6 faces of 2 by 2, which is 24 square meters, is distributed as given in A, B and C. There is a 2 meter by 2 meter surface which is in contact with the ground, which becomes the bottom. There are 4 faces of 2 meters by 2 meters which are in contact with the formwork, and then the atmosphere after the formwork has been removed. And then there is a 2 meter by 2 meter surface which is exposed to the atmosphere on the top, and this B and C finally become exposed to the atmosphere. A is not exposed to the atmosphere. Now, remember these figures, and let us consider the second case, where we are talking about a 200 mm thick concrete slab measuring 6.3 by 6.3 meters cast against the ground. Now, the 6.3 has been chosen for a specific purpose in order to make the volume of the concrete the same, that is 8 cubic meters. So, 6.3 into 6.3 into 0.2 would still give you approximately 8 cubic meters of the concrete. Now, this 8 cubic meters of concrete now has a total area of 84.4 square meters as against the 24 square meters that we had at the previous case. As far as the distribution of this 84 square meters is concerned, there is a 6.3 by 6.3 meters in contact with the ground, which becomes the bottom, and there are 4 faces of 0.2 into 6.3 which are in contact with the formwork and then the atmosphere, and there is a 6.3 by 6.3 exposed to the atmosphere on the top. So, through this top and this bottom, the heat that is liberated in the slab or the concrete which has been used to cast the slab is dissipated into the atmosphere or taken into the ground for ultimate dissipation. As we can see that if there is only a 200 mm difference here, then the possibility or the extent of the thermal gradient that will develop between the core temperature here and the tops or the bottom is quite small. We can virtually assume that the temperature throughout the slab remains constant, and this is an assumption which we cannot make in the case of a block. Let us take a look at the block once again, and this is an assumption which we cannot make for the 2 meter by 2 meter by 2 meter concrete block, where the top and the bottom, they are separated by 2 meters, and the core here is 1 meter away from the nearest surface. As far as of course the slab is concerned, this being a much smaller distance, that is the top and the bottom being much closer, the distance between the sides does not really matter, because as far as heat is concerned, we can assume it to be quickly dissipating in the direction which is closest to the surface. Now, let us take a look at a concrete block which is cast against a glass plate, and there is a certain original length of the concrete block. Once the concrete has been cast, on account of the rise in temperature of the block due to the cement hydration, there is an expansion. So, this original length which was here has now changed to these values on account of the expansion in the block. We have assumed that glass does not provide any friction or restraint, that is, this surface here as far as the concrete is concerned expands to the same extent as the surface on the top, that is the free surface. Once the concrete is cooling, that is the peak temperature has been reached and the concrete begins to cool. After all, the hydration does stop, it does, the heat liberation does not continue all the time. So, after a certain point in time, the block will start to cool, and once it starts cooling, the concrete tends to or wants to come back to its original position, but this contraction is resisted as the concrete has now acquired a lot more stiffness than it had in the initial stages. And this is the kind of discussion which requires us to very clearly understand that the concrete properties every hour, every day are changing, and therefore, the properties of concrete that were allowing it to expand when the heating was going on have changed to the extent that they would resist the change in the opposite direction. So, as a result of which the concrete takes a intermediate position, that is, the length of the concrete from this point in time, from this maximum level has come to this point here and not this point here. So, the concrete which was at A went to B and has come back to C, and the same thing is on the side here. So, once we understand this part, what that means is that there is a final length and there is an original length, and the concrete is under a virtual tensile strain. So, the concrete feels as if this amount of extension in the concrete is a tensile strain, and this can be looked upon as being caused by a virtual tensile stress. So, it is as if there is a tensile stress which has caused or which has brought about the expansion or an increase in the length of concrete to the extent of, if we use the previous nomenclature, it is A and C, that is the original position and the final position. The B, which was the position after expansion, is somewhere here. Now, this thermal tensile stress is related to the modulus of elasticity of the concrete, which again is the property at that point in time. Continuing our discussion, if this tensile stress that the concrete is under exceeds the tensile strength of the concrete, at that point in time the concrete will crack, that is, we will have cracks form like this. And these are the cracks which have been induced by the tensile thermal stresses on account of the heat that was generated when the cement was hydrating, and the heat dissipation was not proper, and the concrete could not come back to its original position, and therefore, cracks. Now, let us consider the concrete being cast in an actual condition and not a glass plate. So, this here represents, let us say, ground or a previously cast concrete, and these are the concrete blocks that we are casting. So, if this is the initial condition of the cast concrete, in this case there is little external restraint, and in this case there is total external restraint. Let us see what happens when the temperature increases, that is, during the rising part of the temperature. This is what will happen to the concrete. The concrete will expand at the bottom as well as at the top, except that the expansion at the top will be slightly more than that of concrete at the bottom, because after all, even though there is little external restraint, we have not said that it is 0. The second thing we should notice is that there is the core of concrete which has been shaded in a slightly different color, and this temperature is not really the same as the temperatures at the top and the bottom. Compared to these set of pictures, let us see what is happening at the other side when we have total external restraint. Now, if there is total external restraint, the ground here does not allow the concrete that has been cast to expand, and therefore, there is no change in the dimension of the concrete at the bottom. And because there is no change at the bottom, this effect is carried over even to the top, and the extent of deformation at the top is also restricted. Now, let us look at what happens when the temperature falls. When the temperature falls, because there is little restraint as far as the picture on the left is concerned, the concrete comes back to its original position, whereas in this case it remains where it is and the concrete at the free surface has contracted. So, this is something which we must understand and keep at the back of our mind, that concrete expands and contracts. The extent of expansion or contraction is governed by the principles of heat, that is in terms of the coefficient of thermal expansion and so on, the amount of heat liberated, the coefficient of thermal expansion, the stresses, the strains and all that, and also related to the degree of restraint that the environment offers to it. And in this case, the environment is primarily the external environment, which is the ground or the base against which the concrete is cast. So, it is not a frictionless surface. So, these things if we keep at the back of our mind, we are prepared for a more analytical or a more quantitative discussion of considerations in mass concrete. To revise our situation, to finally revise the principles once again, there is an initial condition where there is an original length L followed by temperature rise. If there is free deformation, the degree of restraint being 0, the concrete expands as shown up to this point here, and which means that there is a free strain as shown. Compared to this, if the degree of restraint is 1, that is there is full restraint, the concrete remains where it was, and there is a restrained strain equal to the amount of free strain. When there is partial restraint, that is the degree of restraint is 0.3, and that 0.3 means that the restrained strain is 0.3 times or 30% of the free strain, and this is the free strain that we get. Now, this is an illustrative example of actual data obtained from laboratory studies in a block. We will talk about the actual conditions and so on later on, but I thought I will share this with you today to give you an idea as to what is the kind of temperature rise that we are looking at. Let us not bother about the end conditions and so on and so forth. Suffices to say that if we begin with an initial temperature of about 30 degrees, the peak temperatures could be of the order of 60 to 70 degrees. That is, the extent of increase in temperature is of the order of about 30 to 40 degrees centigrade, and this happens within a certain period of time. So, if we look at the peak temperature and when it is reached, we will get this number here. Having said that, finally, the concrete block does go to an equilibrium temperature at the end of a certain amount of time once again, and this process is a lot more gradual. So, this is the kind of actual numbers that we are talking about. Keep that in mind when we study principles of mass concrete. We try to do the analysis, we try to do the design. In this particular module, of course, we will probably not do a very quantitative treatment, but we must remember these numbers and keep them at the back of our mind, so that we are able to at least appreciate the principles of design, the principles involved in construction, where mass concrete considerations are important. Now, simplistically speaking, the problem of thermal stresses in concrete can be studied by integrating the following: heat generation, which is liberation of heat, movement of heat through the concrete through thermal gradients, and dissipation of heat to the atmosphere. So, if we are able to integrate these three ideas that we understand from physics, we can understand how to handle situations in mass concrete, or how to handle thermal stresses in mass concrete. Now, as far as heat generated is concerned, it is related to the volume of concrete and the proportions and properties of the materials used. So, if there is a certain volume of concrete, the amount of heat generated there would depend on what is the property of the materials that you have used, cement, aggregate and so on, and what is the proportion, how much of these individual materials went into a cubic meter of that concrete. Of special importance to us would be the properties of cement, that is the fineness and the composition. The fineness and composition will both be important for us to understand the rate at which the heat is liberated, the rate at which different phases hydrated, and finally, of course, the unit cement content. These are the principal factors that help us understand the heat generated part. Now, if we come to the heat movement through the concrete, we have the properties of concrete such as conductivity and specific heat, which help us understand or model how much heat will be transferred from one place in concrete to another. And another factor is the temperature difference between neighboring concrete elements. If we are using any kind of a finite element or such software, we must understand what is the difference between the temperatures at neighboring points. And once we understand the difference, then we can calculate or model the amount of heat that will be transferred. As an extreme example, it is the core part of the concrete and the surface. So, if we just consider concrete to be made up of a core and the surface, we know how we will try to understand how much is the temperature difference between the core and the surface. Now, as far as heat removal and dissipation is concerned, it occurs from the surfaces, and we must remember that as far as heat dissipation through the surface is concerned, curing is a very important factor. If we put water on the surface, it changes the characteristics as far as the heat dissipation is concerned. So, curing is important, has its implications not only in terms of strength development and hydration of cement, but also in terms of controlling or affecting the thermal gradients, the temperature and so on at the surface. And this amount of dissipation will be different in the case of the bottom of the concrete, where it is cast against the earth or a previous concrete. Similarly, the dissipation will be different from walls, which are initially in contact with the formwork and then with the atmosphere once the formwork has been removed, and the top surface, which is exposed to the atmosphere. So, in these two cases, curing is very critical from the point of view of understanding or modeling the dissipation of heat through the concrete surfaces. It is important that we understand the surface area and surface temperature of concrete through which the heat is transferred to the atmosphere. That also will be an important player in the understanding or in modeling the heat dissipation. The temperature the difference in the temperature between the concrete and the atmosphere, and also the conditions in the atmosphere. For example, if the wind, rain, temperature, all these things would affect the extent of heat transfer that takes place from the concrete surface into the atmosphere. So, once we are doing a numerical model, where we are trying to understand that okay, we cast this concrete block and now we want to understand how soon or how much later will the heat here be dissipated through the surface here. We must understand from number 1, how much heat is being generated here. Number 2, how easy or difficult is it to pass through the concrete, and then what is the properties or what are the properties at the surface. What is happening in the ambient region, wind, rain, temperature and so on and so forth. Now, when it comes to working with mass concrete, how do we handle it? What are the things that are important? We try to control the materials and proportioning of concrete. We try to reduce the cement content to as little as 100 to 120 kgs per cubic meter. This can be achieved through the use of chemical admixtures, air entrainers, or simply, this is a mistake, it should be simply increasing the water cement ratio. So, we use high water cement ratios, maybe even as high as 75–80%, because the strength we are looking for in these cases is pretty small. It could be just 12 to 15 MPa, for example, in gravity dams. So, we use chemical admixtures to reduce the water demand, we use air entrainers, and that also helps us get the water demand down. We try to replace a part of cement by artificial materials such as fly ash. We try to use low heat of hydration cement, and this idea of a low heat of hydration cement could be different in the case when concrete is used in dams and in the case when the concrete has high strength. In the case of dams, we are looking at minimizing the amount of heat that will be generated initially, and we are not particularly bothered about whether or not a large amount of strength development happens later on. In the case of high strength concrete, we are concerned with the strength at the later stages, but also we are concerned with the heat. So, therefore, I would like you to recall the discussion that we had early in this discussion today, when we said that C2S and C3A, they all react and hydrate, liberate heat at different rates, and depending on what we want, whether we want high strength, we are willing to live with strength development taking place later as far as concrete is concerned. We do not want to compromise on the amount of heat liberated. C2S and C3S have to be balanced in a proper manner. C3A needs to be taken out or minimized if we need to do that, and so on. We can use chilled water or ice flakes with mixing water to reduce the temperature of mixing water. Basically, every possible trick that helps us lower the peak temperature should be explored. We have seen that the peak temperature could be as high as 65–70 degrees centigrade. We need to somehow keep it as low as possible, and therefore, we should use every trick there. We use the maximum possible size of aggregate, and this reduces the water demand, and thereby the unit water content, and therefore, the unit cement content for a given water content. Use the largest possible size of aggregate. We should try to arrive at the most desirable or an optimum combination of aggregate sizes, so that the water demand is reduced. In construction of structures like dams, there is so much concrete being used that even a small amount of adjustment can make a large amount of difference as far as the total amount of cement is concerned or the heat generated is concerned. When it comes to transferring the discussion from the temperature to stresses, then the properties of aggregate also become very important. So, we need to study the aggregate mineralogy, and this mineralogy and the aggregate content affect the properties such as the elastic modulus of concrete, which is an important factor in determining the actual tensile stresses in the material. We need to study the properties such as heat diffusivity and the coefficient of thermal expansion, which are also greatly affected by the aggregate. Basically, we should use concrete with the stiffest possible consistency, In fact, given the volumes of concrete involved, alternative methods of placing and compaction should be considered rather than increasing the water content and the ensuing cement content to facilitate construction. And this alternative method of placing and compaction, this discussion has taken us to the roller compacted concrete construction. Instead of constructing dams and such structures with blocks of concrete, the thought process transformed to create large layers of concrete, which were compacted using vibratory rollers. And once the concrete of a block gets transformed into the concrete in layers, then as we have seen in several of our examples today, the problem of thermal stresses can be minimized, if not avoided. As far as lowering the peak temperature is concerned, we need to, or we could try the option of pre-cooling the materials to a lower placing temperature. So, this placing temperature is the temperature of fresh concrete and is related to the proportions and the temperature of the individual materials. So, if we pre-cool the materials, we will get a lower placing temperature or the temperature of fresh concrete. We could also try post cooling as against pre cooling, and post cooling involves running cold water in a network of pipes buried in the concrete to remove the heat generated and reduce the temperature rise. Both these options have been used. Post cooling was first used in the Hoover Dam in the US in the early 30s. So, you can imagine that at that time, without computers, without even calculators perhaps of any form, engineers did use techniques which were highly innovative. Pre-cooling was used for the first time in the 1940s. So, what we are doing now is giving a quantitative meaning to qualitative suggestions or steps which are or which have been taken, which are logical and which have already been taken into our modern day construction, so that our constructions become more effective, they become more accurate, our calculations are more reproducible, they are closer to the actual behavior in the field, and so on. As far as pre-cooling is concerned, it involves use of pre-cooled materials with the intention of lowering the initial or placement temperature of concrete, and has the advantage of reducing the water demand a little bit, which is also related to the temperature of placing being lower at lower temperatures. We could use crushed ice and or chilled water as far as mixing is concerned. We could cool the aggregates using liquid nitrogen, spraying it with chilled water and so on, but for that we need to set up special facilities to pre-cool these materials and lower the temperature to say 5 degrees or 7 degrees and so on. This here is a representative diagram which tells us how does the temperature rise change if the placing temperatures are different. So, if the placing temperatures of concrete are lower, the temperature rise is lower, and so long as the temperature rise is kept in control, the problems relating to mass concrete can be kept in control. With that understanding or with that thought process, we try to take steps in order to reduce the placing temperatures. What is more effective? Water being a higher specific heat than rocks or aggregates, it is more efficient to use chilled water than chilling the aggregates, and carrying this thought forward, we could use ice instead of water for mixing. As far as post cooling is concerned, it is achieved through circulation of cold water in pipes which are about 25 mm in diameter, 1.5 mm in wall thickness, which are embedded in concrete. This helps us stabilize the volumes of concrete, so that other operations such as grouting at joints etc., can be carried out and monolithic construction can be ensured. It helps the concrete to come to equilibrium much faster. Due to the low conductivity, it may take several years to achieve otherwise. So, what we saw earlier, the cooling in the natural course is a very long drawn process, and therefore, post cooling helps us quickly get rid of the heat and get the concrete into equilibrium. What should be the time when the water circulation is started and at what rate should it be done? Now, this is a picture of embedded water pipes, and at distances which is S1 and S2 which is shown. We should remember that once we run the cooling water, there is a region around the pipe which will be cooled by that particular pipe. So, depending on the modeling and the analysis that we do, we need to arrive at these spacings S1 and S2 and also the flow rate of water. The rate of heat removal is obviously related to the flow rate of water in pipes and needs to be carefully designed for the entire purpose or for the entire period of concrete construction. Initially, when the modulus of concrete is low, the heat removal can be as quick as possible. We need to have a flow rate which is able to do that. Later on, when the strength and the modulus of elasticity increases and the peak temperature is reached, at that time the flow rate needs to be adjusted. Continuing with our discussion, as far as working is concerned, we come to some design and quality control specifications. There can be a cap or a maximum limit on the acceptable temperature for individual materials. There can be a cap on the maximum placing temperature of concrete. As we have seen in this illustrative example, we can cap this temperature here, which is the placing temperature. We can cap this temperature rise. We can cap the peak temperature. So, these are some of the specifications which a designer can give as far as prevention of cracking or handling thermal stresses in concrete is concerned. Now, we will continue with the discussion in the next class, and let me give you some material which you can refer to for reading. This is a list of such material, and I would like to thank so and so for the discussion. Before we close, there are some questions which you can take as home assignment. Try to obtain specific information about the heat of hydration of different cements. Study the mixed proportions used for the major concrete dams in the world. Study a case study on pre-cooling and pipe cooling application in concrete construction. Study different specifications relating to concrete constructions using mass concrete. Thank you.